This video, we're going to use scientific notation to help us solve some word problems. So in the first one, it says the national debt of a small country is 6,444,000,000. So we're going to write that as 6.44 times 10 to the ninth dollars. And the population of the country is 2,794,000. So 2.794 times 10 to the sixth people. And we want to break that up into what is the approximate debt per person there. So we're going to take 6.44 divided by 2.794 is 2.304939,155 times 10 to the third dollars per person. And we're gonna, again, this was in 3 sig figs, this was 4 sig figs, so I'm going to make my answer in 3 sig figs. So it's about 2.30 times 10 to the third dollars per person, which means that it's approximately $2,300 per person. That's what that means. If we want to be more exact, then it is $2,304.94 per person. Okay. We'll clear this and come back here. The Earth is approximately 92,900,000 miles away from the sun. So we're going to make that 92.9 times 10 to the sixth miles times, and then a conversion factor here of 1 mile is going to be 1.61 times 10 to the third meters, roughly. So what is the distance to the sun in meters? Let's take 92.9 times 1.61 times 10 to the ninth meters. This is 3 sig figs. This is 3 sig figs. So I should give my answer in 3 sig figs. So that's going to be about 150 billion meters, or 1.50 times 10 to the let's see, 9, 10, 11 meters. The distance from the Earth to the Sun, again, is about 92.9 times 10 to the 6th miles. How long would it take a rocket traveling at distance distance divided by time equals rate? So distance divided by rate is equal to time. 2.9 times 10 to the 3rd miles per hour is going to give us times 10 to the 3rd, 92.9 divided by 2.9 is 32.0344876. This is hours, and we're going to make this into two significant figures because that's the smallest amount of significant figures that we had. This can be 3.2 times 10 to the 4th hours, or approximately 32. Yes, that's it. 32,000 hours. It's a long time, right? Because it's not traveling very fast compared to the distance that it needs to travel, right? If the speed of light is 3.00 times 10 to the 8 meters per second, how long does it take light to travel a distance of 2.29 times 10 to the 11th meters by 3.00 times 10 to the 8th meters per second? So that's going to be 2.29 divided by 3.00 is 0.76333, so on, repeating, times 10 to the 3rd seconds. And we have 3 sig figs here, and we have 3 sig figs here. So we're going to go to 3 sig figs here. And then we're going to write that in scientific notation. So 763 seconds is what that would be. A light year is the distance that light travels in 1 year. Find the number of miles in a light year if light travels. So 1 light year (1.86 times 10 to the 5th miles per second). And we want the number of miles that it's going to travel in 1 year. So we need some conversion factors here. So there's 3,600 seconds in 1 hour. There's 24 hours in 1 day. And there's 365 days per year. So seconds go away, hours go away, days go away. I'm going to take 1.86 times 3,600 times 24 times 365 gives me this big number. And we're going to change that into scientific notation. These are all exact numbers, so they're infinitely many sig figs. So I'm going for 3 significant figures here is going to be about this. And I'm going to write that as 2, 3, 4, 5, 6, 7 times plus the 5 that's already there. And there we go. So I believe that those would be quadrillions. I think would be 10 to the 12th would be a quadrillion. Computer can do a calculation in 1.4 times 10 to the negative 7 seconds. How long would it take the computer to do a trillion calculations? So 10 to the 12th divided by 1.4 times 10 to the 5th, 10 to the negative 7, excuse me, is going to be times 10 to the 19th. Eight, 5, 7, so on. And we're going to make this 2 sig figs because the 1 times 10 to the 12th was exact. So 2 sig figs here is going to be, I'm going to make that 7.1 times 10 to the 18th calculations per second. Or calculations, excuse me. And it would get the 1 times 10 to the 12th calculations done in this many seconds. Sorry, this is seconds. That's a lot of seconds. So assume the volume of the Earth is 5 times 10 to the 14th cubic meters, and the volume of a bacteria is that. If the Earth could be filled with bacteria, how many? So divide here, 2.5 times 10 to the negative 16th. This is 2 times 10 to the 30th. I don't have to do any rounding there because there's 1 sig fig there, 1 sig fig there. How many liters of oil are needed to supply the electrical energy of the average U.S. home for 10 weeks? Assume that the energy released by burning 1 liter of oil is that many joules, and the electrical energy is used. So we need to get this joules per home times this many joules per liter of oil. And so we're going to do that division of the 10 to the 7ths are going to cancel out there. And 5 divided by 1.2 going to be a number a little bit smaller than 5, and it's going to be 4.16 repeating liters of oil per home. And we're going to round that. Again, this was exact, so don't use that. Use this one here. So 4.2 liters of oil per home. If you could generate energy by fusing the hydrogen in ordinary tap water, how much water would you need to meet the energy needs of the United States for 56 years? Assume that the energy released is 7, 10, 13th joules, and that the annual energy consumption of the US is 1 times 10 to the 20th joules. You would need times 10 to the 7th. 1/7 is 0.1428571429. And we're going with 1 sig fig here. So this is going to be 1 times 10 to the 6th. What is that? Atoms? How much water would you need? So it doesn't say what the water is measured. Oh, liters of water. Liters of water. There we go. All right. And last problem in this video. Suppose that we could somehow capture all the energy released by the sun in just 1 second. For how many years could the US energy need be met? So we are going to take, that's our energy need, and we've got that many joules of energy is being released from the sun annually. Other way around. We've got all this energy here. Joules per year. And we want to change that into seconds. So we need 365 days in 1 year. And we need 24 hours in 1 day. Other way around, 1 day. 24 hours. And we want 1 hour is 3,600 seconds. So we need to convert that energy per year for the sun into energy per second, like so. So let's multiply those denominators there. and get something exact. 365 times 24 times 3,600. Denominator there is big. It's going to be 1 times 10 34th joules over 31536,000 seconds. So let's figure that out. 1 second EE is how you do times 10 to the power of in the calculator. 34 divided by that answer that I got up there is 3.170979198 times 10 to the 26 joules per second. All right, now we need to figure out, we're trying to satisfy the energy needs of the entire United States with this rate. So that's 1 times 10 to the 20th joules of energy needed divided by 3.170979198 times 10 to the 26th joules per second. So I'm going to take 1 times 10 to the 20th divided by my answer here is going to give me 3.1536 times 10 to the negative 7 seconds. That's all the time that we would need to be able to capture the energy from the sun to be able to power the US for an entire year if we could capture all of its energy. And we're going to make this into 1 sig fig. So because everything else was in 1 sig fig, there we go. All right, we are done with these word problems. Next time we'll come back and we'll talk about scaling factors.